We are discussing the image classification, data integration and analysis. What is remote sensing? As this phrase says, sensing remotely. So it is a science and art of obtaining information about an object, area or phenomena through the analysis of data acquired by a device that is not in contact. This is important, not in contact with that object, area or phenomena under investigation. So the practice of deriving information about the Earth's land and water surfaces using the images acquired from an overhead perspective, using the electromagnetic radiation in various regions, one or more region of the electromagnetic spectrum reflected or emitted from the Earth's surface. So we have some example like this is a simple photograph, maybe from a digital camera. This is a digital hyperspectral image. This is the Landsat thematic mapper image, and this is the Landsat MSS mosaic, multispectral mosaic. So what are the applications of this remote sensing? Meteorology, that is weather prediction, climatology, oceanography, coastal studies, water resources, geology, archaeology, and land cover and land use. This is an example of land cover and land use. Okay, land cover is the area which is covered by natural being, and land use is how it is utilized. Means there may be trees here, but you are utilizing it as a garden. So that is the land use. Let us see some principle of remote sensing first, because the most important thing is the interaction between the incident radiation and the targets of interest. And there are two types of remote sensing, active and passive. So one is this, that the satellite or the device senses what is being reflected or emitted, or the reflectance from the sun, and this is sent to some station, and then it can be received by the user. So this is the A is the source of illumination. In the passive remote sensing, it is sun. In active, it can be radar. This is our atmosphere. This is the interaction with the target. Here we have the target, and then this one is the recording of energy by the sensing device. This one is the transmission, reception, and processing. Here we do the interpretation and analysis, and finally certain application for strategic or decision making purpose. So we have reflected light. So what is the reflected light? Whenever this light interact with any object or material, there is a reflectance, right? So whatever we see here, this is I. We see whatever is being reflected. Leaf is green because green is predominantly reflected. Others are also reflected, but the green wavelength is more reflected. When it comes to radiance, we can plot the radiance with the wavelength, and also the radiance with wavelength of different material can be seen, and they show their different curve in the various region of electromagnetic spectrum. For example, if you see here, these are the low frequency, means high wavelength, longer wavelength electromagnetic radiations. These are high frequency and short wavelength. Okay, low energy because the frequency is less. High frequency, that means high energy. And frequency is what? Frequency refers to the number of crests or the troughs of the waves of the same wavelength that pass by a point in 1 second. Then we come to the pixel. This is very important. Pixel is what? See, pixel stands for picture element. A picture element. So in image processing term or in an image term, see, this is a green vegetation. This is asphalt road. This is your tile. If you make it over this tile, this is certain dry vegetation. This is concrete. So say this is your image, and we divide it into number of rows and columns. So this one, element in a row or column in a matrix, you can say it is a pixel. Then we come to the wavelength, that is the bands. When the imaging is done, it may be done in various bands, and this band only means that the wavelength in which the reflectance is being taken. So these are various areas or places where the reflectance has been taken, and that can be, say, near infrared, it can be shortwave infrared, and our visible band is from 0.4 nanometer, this micrometer, to 0.7 micrometer. Above 0.7 there is reflected IR, and 3 to 5, and then we have the 8 to 12, we have the emitted energy, that is the IRML energy. What about the band combinations? If you take the 1, 2, or 3, these bands from the various, because normally the satellite imaging is done in various bands. So when you combine 3 bands, you can get a better idea. This is how 432 band is combined. This is the 543. Then feature space image. This is a graphical representation of the pixel by plotting one band to other band. For example, say a 6 band Landsat image, there may be 15 feature space. So this is the plotting of different bands, and you see that this is how it varies. And these are the pixels, and you can find the various phenomena here occurring. You can find the correlation, you can find the variances. So each color represent a different cluster pixels that may correspond to the land cover classes you are interested in. And this is a very famous software used in mostly in vector processing, that is RQ. You see a classification result here, the different classes are being shown. This is the majority filter of your supervised image. Supervised image means you have done a supervised classification here, and supervised classification means you have chosen a pixel by yourself. That means you have given trained a sample by yourself, and that sample, according to that sample, some algorithm has done some work, and this is what you have got. So in image classification, the question arises is why to classify? Because we want to make sense of the landscape, the place landscape into different categories, because we know in the real world, this is our marshy land, this is our urban land, this is our water bodies, like the forest, agriculture, water. Then there has to be a classification scheme. That means you have to make a scheme. That is how you are going to divide it into various clusters. That is, the structure of cluster is to be defined. And this actually depends on the needs of user. If you are an urban developer, you will be interested in more in the urban things, like the small land areas, large land areas, and the big man-made architectures, the high-rise buildings, the low-rise buildings. All these you are interested in, and this can be different from for some other person who is interested in some other thing. So what is a classified image? When the image has been processed to put each pixel into category, that is the classified image. The result is, say, a vegetation map. It can be a land use map, or it can be another map with certain feature you desire. And the categories are defined by the intended use. As I am saying, it depends on you. And it can be a few or many categories. You can just divide in 3 categories, and you can divide in 30 categories, depending on the purpose of the map and the available resources. So land cover classification, if you see this is the land cover classification. As I just said, that the land covers are those surface contents which are covering the land. Is the bare earth. So it can be desert, it can be greenery, it can be some water. So land cover classification step involve, first we have to define why we want a classified image, and how are you going to use it. So decide if you really need a classified image. For that you have to define the study area, because an image can be large. You are interested only in this region, so a study area has to be defined. Then you have to select or develop a classification scheme, how many classes you want. Then you have to select the imagery, because imagery is important, because classification will be done on the imagery, and that those imagery pixels will be classified. Then you have to prepare imagery for classification, and if ancillary data is available, collect that data. Choose the collection or this collected ancillary data. After that, the method you need to employ for classification, and then you adjust the classification, and then you can use the accuracy like kappa, coefficient, etc. So in the image classification, this is an example of image classification. See, these are various ways in which you have classified. You can use the different bands, and basis of your categories which you have defined, you can classify it. So the uses are, it will provide you a context, that is the landscape planning or assessment for research products, and you can also use it to drive models like the global carbon budgets, the meteorology, the biodiversity. So application in agriculture, as you see here, that we want that what was the previous one, what was now, and you also want to see that which area is infected, which is good. So this one is a color infrared photograph of big lake. This one is a classified image of big lake. This one is a quick bird image of big lake, that is 0.6 meter resolution panchromatic, and this one is a classified satellite image. So the basic strategy is, how do you do it? We use radiometric properties of remote sensor. Different objects have different spectral signatures. This is important. Every object has a unique spectral signature. For example, if we take any band, the vegetation and soil will vary like this. Vegetation, you see, here we have peak in band 4. So if you are interested in vegetation, why not to try for band 4? And likewise for other bands also. So in an easy world, all vegetation pixel would have exactly the same spectral signature. Then we could just say that any pixel in an image with this signature was vegetation. I will do the same for the soil and end up with a map of classes. Okay, now image classification. This is an example of just a simple classification. These are your classification classes. This is your input digital data, and after classification of process, you'll get a thematic, because you'll just get a thematic map. Classification gives you a map because this image has been classified. Now you get the classified data. In the classified image, see, black is water, yellow is open. This one is the open field. You can see the light green is the sparse forest. This one, and the bronze is your mixed urban. This one. And the red, of course, this is the dense urban. Now you have to perform the query. So how you will formulate this? See, you want to query a patch pertaining to some semantics, like mountains you want. And this is the satellite image database you have. And these are the results ranked by their accuracy and precision. In the geography, we want to find mountainous region with snow caps. This is low level semantics. In forestry, we want to find forest of certain density and analyze the deforestation. This is mid-level semantics. And when it comes to high-level semantics, in military applications, we want to find air bases in certain regions of the world. So basic strategy here is dealing with the variability. In the classification, we delineate the boundaries of classes in n-dimensional space. We assign class names to pixel using those boundaries like this. Okay. This is one. This is another. What about information classes versus the spectral classes? See, information classes are categorical, such as the crop type, forest type, tree species, different geologic units or rock types. The spectral classes are a group of pixels that are uniform. Information classes are categorical. Spectral classes are uniform or near similar with respect to their brightness value, their spectral signature in the different spectral channels of the data. So, two basic strategy for classification is supervised classification. So, we impose our perceptions on the spectral data because we are aware and we have a priori knowledge of that area. In the unsupervised classification, the spectral data imposes constraint on our interpretation. We are not aware, so let us tell the computer or the algorithm or be dependent on what the classification will give us. So we have classification. Let us decide. We want to do the supervised classification. We want to do the unsupervised classification. If we are doing the supervised classification, we can have two more children to this tree. First is your distribution free. The other is statistical technique. In distribution free, we have Euclidean classifier, k nearest neighbor or nearest neighbor, k means you can say, the neighbor, and the minimum distance and the decision tree. So these are the supervised classification, distribution free. In this statistical technique, this is based on the probability distribution model, which may be parametric or non-parametric. Parametric and non-parametric means whether you are using statistical parameters or not. In the unsupervised classification, we also call it as a clustering. Unsupervised classification, also known as clustering. So we have no extensive prior knowledge. Okay, so we have spectral classes. They are unknown, but they are distinct, and these are generated by limited control over classes and identities, and no detailed information is available. So these are the methods you can use. Unsupervised classification and supervised classification. What you do in unsupervised? You separate data into groups with clustering. Classify data into groups, assign name to each group, and then if it is satisfactory, okay, otherwise you reiterate the things. In the unsupervised classification, we form images of data. That is, you choose training pixels for each category. You calculate statistical descriptions, and then you see whether they are satisfactory or not. If they are satisfactory, you say we classify the data into categories defined. In the supervised classification, this is your image data set. Okay, these are the classes. You know that what are the classes. So what you do here is, you have a training stage first of all. In the training stage, you give the digital numbers or the spectral signature of water, sand, forest, urban, corn, hay. And then this image data is subjected to this these supervised or these already trained, or you have taken these samples, and then this is the output stage, and then you go for the accuracy. So, for example, this is, say you have chosen a region of interest, small region of interest, or the training sample. You say this is rock, you say this is my water area, this is the agriculture area. And when you combine this, you say these three classes will be given to you. So supervised classification requires the analyst to select training areas or training sets where you know what is on the ground, a priori knowledge, and then digitize a polygon within that area. So you know that conifer area here. So what you do, you take that particular part. The computer then creates what? A conifer. So you have taken that spectral signature and you have devised that, okay, this is the area. So computer what does? It creates a mean spectral signatures of this area. And if you have a known water area, you choose this, and then it again creates water. You know the deciduous area, the computer is going to create a deciduous mean. So this mean spectral signature, these are the mean spectral signature, and you have a multi-spectral image. So this is known and this is unknown. So we match this with the unknown with which of these are matching. And once this is matched, we say the spectral signature of next pixel to be classified, and this is our area. This is how we classify it. So we have to take an area of interest. That is the detection of geometric features like buildings, like high pass filtering and thresholding you use, the template matching you do, the temporal change in the temporal change detection. We can use the subtraction, the ratio, the correlation, and the comparison of classified image also. So this is a simple line detection filters. You can see the various filters are available like the cannies, the sobels, and the privets. So in the image segmentation, we detect the homogeneous surfaces, and we use here the thresholding or edge detection. And also we have region growing algorithm. Okay, so this is you can just use the high pass or standard filtering or either NDI also. This is the line detection filter. Line detection means it will detect only the lines, these two to two wherever they are, whether they are in diagonal or reverse diagonal or the horizontal or the vertical. It will try to find out the lines. In terms of averaging filter, all these value will be added. This is the you can say a kernel which will be passed, and in average value will be provided to the central pixel. This is the thresholding. Any value below x will be provided given some value, or any values, all the values which are above x will be given some other value. You see, this is white, this is black. So it is actually delineating your foreground and background. In the supervised classification, as we just said, we form images of data, choose the training pixels, and this is the training part. This is a very important part. In the training areas, what you do, you take the places, or you train, and depending upon the area you know. So the supervised classification, what you do the segmentation here. That means you are not aware of the places, but in the supervised classification you are aware. So what you do, you have chosen the training samples. Now you do the segmentation. That is, you segment the area. So what are the common classifiers here? You can use the parallelepiped, minimum distance to mean, and the maximum likelihood. So in the supervised classification, parallelepiped, minimum distance to mean, and maximum likelihood are the major ones. So the statistical approach in supervised classification, as we said, minimum distance to mean. So what you do here, we find mean value of pixels of training set in n-dimensional space, and all pixels in image classified according to the class mean to which they are closest. That is the minimum distance to mean, like this. So this is the area, a mean to which they are closest. In the parallelepiped approach, what is the pros? It is quite simple. It makes few assumption about character of the classes. So these are the parallelepiped. You make a parallelogram or parallelepiped, and those pixels which fall in this area are classified. In the supervised classification, as we just said, these are the signature comparison result. These are the signature which you employed, and now you have got the result. In the minimum distance, what happens? All regions of n-dimensional space are classified. In the minimum distance, all regions of n-dimensional space are classified, and it allows for diagonal boundaries also, and hence no overlap for classes, as we have seen in parallelepiped. In the maximum likelihood classes, if you see, this is the relative reflectance, and these are the various bands. So you can find in the maximum likelihood classifier the different regions. This is mean signature 1, this is mean signature 2 or 3. So this is the candidate pixel, and this is the mean signature 2. So where it is going to go? So it appears that the candidate pixel is closest to the signature, this green one, that is mean signature 1. So however, when we consider the variance around the signature, we find some other thing. So in maximum likelihood classifier, say if we have this candidate pixel, what we do here is the candidate pixel clearly belongs to the this second group. That is why the maximum likelihood is taken. So in addition to the to classify image, you can construct a distance image. For each pixel, we calculate the distance between its position in n-dimensional space and the center of class in which it is placed. And these regions poorly represented in the training data set will likely to be relatively far from the class center points. And this may give an indication of how well you get your or you train the samples of landscape. So some advanced technique in supervised techniques is neural networks. It uses flexibility. You don't have mostly the linear functions to partial spectral space. You can also have contextual classifiers. This incorporate the spatial and temporal conditions. Then you have linear regression. That is, instead of discrete classes, just apply proportional values of classes for each pixel. Say 30% is the forest, 70% is the grass. So we have decision rules in spectral feature space. This is the parallelepiped. See, these are inside the parallelogram. This is minimum distance to mean, and this is the maximum likelihood. That is the discriminant analysis. In the classified image, you see now this is the actual classified image. In the unsupervised version, unsupervised classification, these are the DN numbers. When we pass it through the algorithm, that is the unsupervised classification or clustering, these are the spectral classes, and then it will be classified. So what happens here is, in a unsupervised classification, the spectral data imposes constraint on our interpretation. How? So rather than defining training set and carving into pieces of n-dimensional space, we define no classes beforehand, and instead we use the statistical approach, which is inherent in the data, to divide the n-dimensional space into clusters with the best separation. And after this, we assign class names to those clusters. So this is how it is done. This is clustering part. So the analyst requests the computer to examine the image and extract a number of spectrally distinct clusters. This is an image. We get various clusters. Say 1, 2. Say we want 6 clusters. So these are the 6 clusters with different spectral signature. So this is the output classified image. But the next pixel to be classified, if it is unknown, we can just check it that which one is the best one. So the result of the unsupervised classification is not yet information until the analyst determine the ground truth for each of the clusters, because blue can be water, or blue can be any other thing. Okay, you cannot say that this light green or this dark green is which one is the conifer. For that you need the reality check. So it is a simple process to recode the cluster into meaningful information classes now. You can just combine them if you are aware. You can combine these two, you can combine these two, you can combine these two. So the result is essentially the same as the supervised classification, but with more statistical information which has been taken out from the image. So this is the n-dimensional representation of the clusters, you can say. So how to evaluate signature? We have signature ellipses. See, these are different bands. And when we compare these bands, they don't overlap in bands M and N. So these are the various signature, we have got from different bands. So there are various errors which may come. Acquisition, that is geometric aspect, sensor system, platform, ground control, scene consideration, and then comes to the data processing. There can be geometric rectification, radiometric rectification, data conversion. Then the data analysis. You can do the quantitative analysis, classification system, data generalization. These are the sources of error. And then the data conversion. This is the most, these two creates most of the error. Raster to vector, vector to raster. Then the error assessment. You can use the sampling error matrix or location accuracy. And final product presentation, you have to say what is your special error and thematic mapper. And then finally, the decision making and the implementation, and error propagates like this. So you have to check what is the error and what is the actual data. So after what you have done, there is a post classification sorting which is called the labeling. So you can just combine them into class 1, you can combine these into class 2, these into class 3. This is how you combine. In the unsupervised classification, what are the pros? We take maximum advantage of the spectral variability in an image. The cons is the maximally separable clusters in spectral space may not match our perception at all of the important classes on the landscape. So the result from clustering, this is the spectral class of unsupervised classification. In the data analysis, the input data is a digital data, so image rectification, restoration, geometric correction, radiometric correction, and noise removal is done. This is I equal to Yij. Yij is a vector representing the intensity of the bands, say RGB for the pixel Ij. And then we do the image enhancement in data analysis. The objective is to create new images from the original image data in order to increase the amount of information that can be visually interpreted from the data. This is how you do. You find the differences, and then you can eliminate the error, or you can actually want to enhance what you want to see, then you come to image classification. So we have ISODATA procedure also. This is the arbitrary cluster means here are established. The image is classified using minimum distance classifier. A new mean for each cluster is calculated. The image is classified again using new mean clusters, and this is done again and again. Another new mean for each cluster is calculated, and the image is classified again. And after each iteration, the algorithm calculates the percentage of pixels that remain in the same cluster between the iteration. When this percentage exceeds t, that is the convergence threshold, the program would stop. And if the conversion threshold is never met, the program will continue m iteration and it will stop. So in this ISODATA, a special case of our minimum distance clustering, this is nothing but the iterative self-organizing data analysis technique. Iterative self-organizing data analysis technique. The parameters you use is n, that is the maximum number of clusters that you want. T is a convergence threshold. M is the maximum number of iteration to be performed. So these are the ISODATA clusters. You start with this initial clustering like this. Then these clusters change, and finally you'll get the final cluster. Iterative self-organizing. So the pros and cons of ISODATA. This is not biased to the top pixels in the image as sequential clustering can be. It is non-parametric. That is, data does not need to be normally distributed like this. Very successful at finding the true cluster within the data if enough iterations are allowed. And cluster signatures saved from this ISODATA are easily incorporated and manipulated along with the supervised spectral signature. And this is slowest of the clustering procedures. So let us have some final thoughts. Classification are never complete. They end when time and money run out. Classification is iterative, that is, it loops. It's tough to get the first few iterations. We consider hybrid classification, that is partly supervised, partly unsupervised. And manual classification or editing is not cheating. These are the examples of Landsat ETM, digital color infrared. And this is the example of Landsat thematic mapper. This is the classification result of Landsat MSS. This is the example of Corona, that is the panchromatic black and white film. So we have examples of classification result. We have already seen this. Just have a look. This is how we classify the scene. So there are some sample patches also for car, pavement, road and tree you can use. This is all about the classification. Hope you got the basic idea. Thank you so much. Take care.